Hi everyone, and welcome to a new episode of Algorithmic Gems. In this series, I talk about advanced algorithmic ideas that aren't usually captured in textbooks. I try to keep it simple and light, but feel free to leave a comment if you have a question, and I'll make sure to reply to you. Alright, let's get started. Today, I'd like to talk about a couple of common techniques that help improve space complexity. Sometimes your solution to a problem doesn't work because it requires too much memory, or sometimes you want to save on resources. In those cases, the two ideas I discuss here might help. So, the first idea to optimize memory usage occurs when you have an iterative algorithm. So, you iterate to do some calculation. In some cases, you can allocate memory just enough for one iteration. Then you can recycle and reuse it in subsequent iterations instead of allocating more space. For example, consider an iterative solution to calculate the nth Fibonacci number. Basically, it starts by calculating the first Fibonacci number, then the second, and so on, until it reaches the nth number. Now, an inefficient memory allocation strategy is to allocate an array of size n to store the Fibonacci number at each iteration of our algorithm. Why is this inefficient? Because at each iteration, you really only need the value of the last two Fibonacci numbers. Anything prior to the last two Fibonacci numbers won't be used in this iteration or any subsequent iteration. So, a much more efficient strategy is to allocate memory only enough for one iteration, in our case here just 2 units for the last two Fibonacci values. Then we can recycle and reuse this allocated space in every iteration. This results in only a constant space complexity. As a second example, let's imagine we have a two-dimensional grid of n rows and n columns, and our algorithm iterates over the grid top, bottom, and left to right. At each cell, you calculate a value that only depends on the cell directly above it and the cell directly to its left. And at the end, you only care about the value calculated for the bottom right cell. So, how much space would we need for such an algorithm? Again, a naive answer is to use a two-dimensional array to keep values calculated at each cell of our grid, which gives us a quadratic space complexity. The question is, can we do better? Yes, we can. Since at each iteration we care only um, about two previous cells, and both have been evaluated in the last n iteration of our algorithm, then we can simply only keep around the values of the last n iterations, so nicely cutting our space requirements from quadratic to linear. Alright, the second idea I will talk about today for optimizing space complexity is applicable when your algorithm has a notion of a state and it needs to process many of those states. This is very common in recursive and dynamic programming algorithms. Typically, you would define a state by a number of identifiers. For instance, if our state is a point in a 3D space, then we can identify the state by three numbers, x, y, and z. Now, sometimes it happens that you have additional knowledge about the problem in hand, which might allow you to reduce the number of identifiers that uniquely identify states. For instance, if we continue with our example here of having the state be a point in 3D space, and we happen to know that any valid state for our purposes must have the value of x plus y plus z equal to 0, then we can uniquely identify any valid state by the value of only two dimensions, say x and y, instead of three dimensions, since we can always infer the third number given the other two. So by having a smaller set of identifiers, we reduce the number of states our problem can have, and accordingly the amount of space required to store values for all those states. Alright, that's all for today. I hope today's topic was useful. If you want to practice these ideas, try to solve the problems in the description of this video. As always, I'd love to hear your feedback or any question you have, and feel free to share this with anyone who might find it useful. Till next time.